Because they saw me start the broadcast. Is it in presentation mode?
Yes.
No. Why can't I do it? Wasn't it working before? Oh, there we go. Yes. Okay. Okay, well, first of all, I have to say I'm so excited that all of you guys decided to come today. So today our topic is going to be introduction to time series. So by raising hands, I just like to kind of pick. So I see some faces that came to my first one, a lot of new faces, so that's like super exciting for me to know that people are able to make it down here. Are most of you from Orange County, or did someone come from far away? Anyone from LA? No, okay, so, okay, okay, that's a minute.
I come here for work. It was a nice talk.
Okay, awesome. So that's exciting. So to me, this looks like we're going to be able to really build a community down here. So I wasn't too optimistic because I was my first one. I mean,
Not supposed to say that. Give it away.
I just wasn't sure. But I know for me, this is really exciting. So I'm really happy to have you guys all here, see, so, you know, like start to get to know your faces, get to know each other, and work off of each other's energy and help each other. So today's topic, like I said, so introduction to time series. I think this is a really exciting topic that I find is really useful and practical to be aware of. And time series data is prevalent in a lot of different industries, so definitely a good topic. So some quick announcements. So I'm not going to be delivering the talk today.
Don't all leave at once.
My co-organizer Eric is helping me with this one. I did the first talk on sampling techniques. If you are interested in sampling techniques and dealing with imbalanced data, I have the recording for that on my channel, so I can post it on the meetup page for this event. This talk will also be recorded, so you can watch it later. But a few things, so I always want to thank Mobility Aware, our programs hosting us, and I think they're doing a really good job helping us. And I work here, I love it here, a few of my colleagues are here, so get to know us. This is an awesome place to work. We're hiring, always looking for top talent, so if you find an open rep position, I mean, just apply, let me know, so I get the bonus. So that would be cool. So for the next two meetups, I think our plan is to kind of dabbling with data visualization as a topic, portfolio optimization, and loss function. So we'll kind of either do one of those, and then maybe this was meant to be the first talk in time series of a series. So we'll eventually continue the time series talk, but it'll probably be in the start of the year. So after September and October, we'll kind of pause November, December, it's holiday season, and then we'll start back up in January. And then also, if you're interested at all in starting your own study group, so it doesn't have to be something formal like what we're doing here, but like even being at a coffee shop on the weekends, or just starting a group that you guys can start talking about, whether it's machine learning, time series, Python, R, anything that you're interested in doing. I know we have a very strong meetup group called Learn Teach Code in LA, which is where I started my initial meetups. So if we can start creating a community down here and building, kind of a support group where we can talk about things as we start learning them. Because data science field is so broad, and there's so many tools and so many different techniques to learn that having people you can talk to and collaborate with is exciting and keeps you motivated. So if you're interested in starting your own underneath kind of the OC Data Insights group that I started, just let's start a conversation and see how we can maybe start it. Cool. All right. And that's that. So how many of you work as data scientists right now? Okay. A few. Data analysts. Okay, great. Software engineers. one. What are the rest of you have to do? Just chat it out.
Good job.
Looking for a job. Okay, good. Well, students? Okay, cool, awesome. In terms of your familiarity with time series, so has anyone worked with time series or is familiar? Okay, all right, so I'm hoping that, again, like I said, this will be the first talk of a series of talks in time series, so this is meant to lay the foundation and the groundwork for future talks. So, so hopefully you'll get something out of it today. And
Wow, pressure.
take it away.
Never preface a talk with saying, I hope we get something out of it. It's never a generally good idea to approach things. All right, so how many of you were here for the first meetup? So just a couple. Very cool. So as long as you just continue to increase the attendance, that'll be good. So I am a principal data scientist at CoreLogic in Irvine. So CoreLogic is not called a household name, mostly because it's a B2B company, but we do a lot of real estate, property type data. Every time you apply for an apartment, you go through the data that we have. So we do a lot of analytics related to that. And we are also pretty consistently hiring across the data science team. So if you're interested or have questions, feel free to follow up with this. All right, so before I jump into talking about time series, I think it's useful to think about why would we care about it? So I'll take you to a situation that inevitably, if you communicate with people within a company, you're going to run into. You're going to go into an executive level presentation or an earnings call or something like that, and they're going to be looking at a bunch of points, and they are going to be going, look, points are going up, the points are going down, nothing's changing. So when they do that, really, I can't emphasize enough how many billion-dollar decisions are made essentially every day by saying, hey, it looks like it's going up, or it looks like it's going down. I have a lot of friends who are traders on Wall Street, and if you look at how they decide whether to buy or sell a stock, they will talk about the elbow in a time series. They'll be like, oh, well, it was a 2 elbow week, so I did this. What are you talking about? So the reason that I think time series are so important, in some ways, they're different from the curve fitting that we're used to in a lot of situations. Time series, you can think about it as we're trying to use the observed data that we have to try to understand what process actually generated the data that we're seeing. We care about what that underlying process is. It's not necessarily being able to fit a curve. So we're going to reference, we're going to have some code embedded within the presentation. So this is just built within Markdown, so we don't have a separate notebook for coding today. But in terms of resources, and these are mostly a function of what Sarah and I think are useful. I should say me, I don't know if I'm describing this to her or not. But I think one of the best books you can start with is Forecasting Principles in Practice. It's relatively straightforward, it's pretty easy to read. It doesn't dive super deep into a lot of the technical, it doesn't present you with a lot of mathematical proofs, which I know everybody loves seeing. Coming from a math background, I don't mind those, but everybody else in this field, never. Time series analysis and applications of our examples, again, is another great text. So these two are both, Sarah's the second one available online. See, I called her out. When you're not paying attention sometimes, it's fun to just call people out. So, the second text, is it available online?
Yes, all of them are available online.
Okay.
I'm going to post these slides, and they'll have link outs to the actual text and to the documentation of that package.
So I recommend this as a starting place before you dive into more of the theory, more of the really heavy modeling texts that are sometimes recommended in other places. So in terms of what we want to focus on today, trying to define what a time series is and what it means to develop a time series model. This is, I think, typically when people talk about time series, they don't ever answer this question. Like, oh, we just do time series, but it means something a little bit different. And I'm going to put on my teaching hat in a lot of ways, because when you see time series, people are very tempted to immediately talk about their real modeling. Like, yeah, just do auto data real and R, fit the most complicated model that you can. But the issue is you don't necessarily know what's going on. Like, how is it fitting this? What assumptions is this modeling process using? What are the processes that actually generate the time series? And so the fundamental building blocks of time series we're going to talk about are white noise, moving average, and random walks. And these cover a lot of things that you see as time series. So those of you who are interested in stock markets and stock, random walk is a very common way to model those time series. We'll talk a little bit about something called stationarity and why it's important. And I'll close with an example which tries to articulate why, in some cases, the idea of curve fitting, we're so used to seeing points and deciding which curve fits all of these points the best, why it might fail in certain situations with time series. All right. So it's really fun. Definitions are fun, right? Sarah bolded these just so you would feel like you're in a textbook experience. But for now, let's work with the time series definition. It's a sequence of values of a variable at equally spaced intervals. That can be adjusted a little bit depending on the modeling process you're using, with a natural temporal ordering. What does that mean? I know, it's like words. Word bound. Okay, so what would be an example? When we say equally spaced intervals, what am I talking about? Yeah, time. Every minute time, right? So you're looking over equal intervals. It could be a second, it could be a millisecond, it could be an hour, whatever it might be. But we care when we're doing this this modeling process that we're working with equally spaced intervals. And when we say natural temporal ordering, right? That just rolls off the tongue, right? Natural. What does that mean? Temporal order. Yes, you can look at an event and say it happens before or after another event. Okay, so definitions are not that much fun, but if we don't have them in place, it's very difficult to speak about everything else. So this is just a simple example of a data set that comes from the package that we described before. So this is looking at, what are we actually measuring, Sarah? I'm sorry, do you remember?
Earnings per share.
Earnings per share. See, that just, all right, we're all over it. Okay, so earnings per share. And we're looking back over a period from 1960 to 1965 and quarterly, right? This is very common for reporting EPS. And if you look at this, so we can plot the time series, and the code is just up here, relatively simple, and this is all done in R. And something that I will say, I will express a personal bias. Most of the time series modeling that I've done and I prefer to do, I do in R. That doesn't mean that I like R for everything, but I tend to find R is better built for time series modeling and time series visualization than a lot of things in Python are. That's my personal bias, so I'm not going to fight it out if you want to say that Python also has a lot of capabilities. It does, but I tend to think R, at least for me, is a little more intuitive in terms of doing this type of work. So if you look at the earnings per share and you show this to people, what are the things you think they notice right away? It's going up, that's good, right? Well, it's going up. How is it going up?
Looks like an exponential growth.
Exponential growth, right? It seems reasonable that like by just looking at this exponential curve might actually fit this data easily. Of course, we would like this actually to be exponential growth over time, right? That would be great. What other things do you notice? Increasingly erratic. Okay, so what makes you say increasingly erratic?
The space, the distance between two consecutive measurements is getting larger and larger in general. Okay,
So you're saying as we jump from here to here, so if we look back here, right, the variability between observations, and then up here, over equally spaced intervals of time, variability is getting a lot larger. Okay? So is that good? Bad? Would you invest in this? I don't know. We're not going to go that far. But there are different ways to think about trying to model this process over time. If you were to take the approach of fitting a curve, right? We decided to fit an exponential function to this graph. That would probably work, right? I mean, and by work, I mean it would produce a solution. So what are the positives and negatives in that case of using an exponential function to fit this, right? You could just imagine it would be beautiful. You go straight through the center of all of this. What are the upsides and downsides of using an exponential curve in this situation?
Does the seasonality come?
Yeah. So say a little more when you say seasonality.
Fourth quarter earnings are always growing.
Yes. Okay, so you can start to see it's much more pronounced once you get past 1975, but fourth quarter earnings are a lot lower. The EPS is lower. So we see something that happens regularly. When we say seasonality, in this case, we're talking about it as a quarterly pattern to everything, right? So the exponential curve would do, would you say it would do a decent job, or would it just, what are your thoughts?
Just not making an average. It would do well for like 8.
Yeah.
Not something that does not get it well quarter by quarter.
Right. It might capture like year-over-year growth, okay? But it's almost no matter what, it's going to miss and not be very accurate if you look quarter by quarter. Right? So this is where this idea between are we curve fitting or what's this, and this is where something like time series modeling comes into play. So another example, we're going to look at another data set. And we're looking at yearly global mean land ocean temperature deviations. Again, it's very straightforward to say a lot of words back next to each other. And we're measuring in degrees centigrade, so from 1880 to 2015. Okay. So we're looking at what we see here, right? So let's think about what's on the y-axis. So what does that represent? Global temperature deviations. What does that mean? 0? I'm just kidding. So global temperature deviations. If we have something at 0.2, what does that represent? Goes up by 0.2. Over what time period?
1 year.
1 year. Okay, so we're looking at deviations. What do you notice about what we see here? What's happening? Like we saw a nice exponential, or immediately thought, yeah, that was sort of exponential last time. What does it look like here? Anything? So we could fit, again, something that I often hear people say is, oh, we can't fit that type of model. Now, you could definitely fit an exponential model, so you can fit any type of model we want to. It doesn't mean it's something good. Okay, so if we were thinking about curve fitting, what difficulties would we run into if we were trying to fit a curve to this data? Can you say a little louder?
It's not a single curve for the entire group.
Yeah. right? If we look at up to 1940, right, the behavior is quite different, or appears to be quite different from looking at 1940 and after. So you might think about fitting multiple different curves, but it's very unlikely that a single curve is going to give you anything very useful in this case. So something that, and again, we have the code up here, and I will go through it as needed. But what we are doing right here is we care about consecutive observations and how they're related to each other. Okay, so if you're in a situation, so how many of you have done linear regression, fit a linear regression model to something? Yeah, or at least heard about it. Okay. There are a few key assumptions when you're doing linear regression. What are they? I know. Right. One of the key assumptions is the independence of observations. Okay, so when you're doing modeling, you're doing things like regression, you are assuming that, at least, I say mostly assuming, that the observations are independent of each other. In a time series scenario, let's think about the stock price and the earnings per share. Is it a reasonable assumption that the EPS measures are independent of each other? No. Why would they not be independent of each other?
It's a relative measure.
Say it over again.
It's a relative measure. Each data point is based on the previous state.
Right. So for them to be, for EPS to be independent, you would have to say the EPS, earnings per share in Q4 1 year, is completely independent or unrelated to the EPS in Q3. That's not a reasonable assumption to make, right? So something that we can see in this example here, where we're looking at, we're fitting a linear model and we're looking at the correlation between these points. You notice we have a correlation of 0.944. Like good, good. It's too good, right? So that says that one individual point gives you a lot of information about the point next to it, and subsequently like that. In a situation where we have independent observations, we would assume that one point doesn't tell you anything about what the next observation is going to be. So think about a situation in which something would be independent. Having taught stats for years, every time I teach, I hate people that use the coin flip example, but guess what I'm going to do? Use the coin flip example, because guess what? It's the one that people relate most easily to, right? No matter what. So, coin flip, what comes up on one coin flip should not tell you anything about what's going to happen on the next one. Unless you're in Vegas and you watch people who think, oh, it's come up red 9 times in a row, it has to come up black next time, so I'm going to bet at 10 grand on black. But humans also assume that they're like see patterns. I'm not going to go on a gambling tangent here. I did that enough on these stats and students. I think they were somewhat concerned that I was like flying to Vegas on the weekend and having too much fun. So if we look at, so let's go back here for a second, sorry. So let's take a look at the code for a second. When we say unclass, has anybody ever used R or used unclass? What does that do? Beautiful silence. Beautiful silence. Sarah, what does unclass do?
Oh, so when we're importing the package ANSA, it comes with preloaded data sets that we can work And specifically, if you look at JJ is the Johnson & Johnson data set. If you look at the class of Johnson & Johnson, it's going to come up as a time series. If you want to work with, like for example, to use the lag function, you're not able to just throw in a time series. It has to be an array. So unclass will take it from a time series type to an array, and then we can use the lag function.
So if you had to make a guess, looking at this code, so we unclass, we changed JJ from a time series to an array, and we're applying a function called lag. What do you think lag does? Just some context clues. We are applying a lag of, there's some parameter that we're putting in that we're specifying as 1. What do you think this function does? Okay, so it makes a comparison of one observation versus the previous observation, right? Okay. So if we are looking at, so when we say LM on this third line, so we have two objects now. We've taken JJ, we've turned it just to an array of observations. We have also created an object called lag. And now we are building so LM in R represents a linear model. Okay, so we're doing a linear regression model. So when we build LM, we're regressing the observations from the time series against the lag. Okay? So this again is not intended to be an entire chart. I love stats, and so I just often will go off on tangents, so interpreting output and things like that. But what we're able to do after creating this linear model is we're able to look we're able to also look at the correlation here. We can do a correlation test, which is what we're seeing down here. And so this is telling us that essentially one observation gives us tons of information about what the subsequent observations. But what's very problematic here is that when we're building linear models, and we're going to dive into this example at the end, when we're building linear models, it's very easy to just build one, right? You can apply code to something, you can run a linear model. It's not going to return an error and say, no, you've done something that's not correct. You haven't met the assumptions that you need. It's going to tell you, it's going to give you output. But the output is not going to be correct, precisely because of that correlation between observations. This is something that you'll run across a lot. I've spent enough time reviewing academic papers, like actually as a reviewer, to where people apply procedures to things without checking assumptions. And it's not like their code doesn't run. Their code runs every time. Gives them the estimates, which they then report in the paper. But what they should have done is actually assume, should I be actually running this model? Okay, so checking these assumptions is very important. All right, so time series, I think for most, it's interesting because I spent a lot of time in grad school and afterward working with data, and I can tell you, it wasn't until the last class, the second time I went to grad school, that I actually learned anything about time series. I had probably taken 15 or 20 courses in statistics and experimental design and things like that, without ever running into time series. Talked about machine learning, talked about regression, talked about every survey design, sampling, everything you could want. But then the one thing that shows up the most wasn't until the last class of the time I did a master's in business analytics. So that's, if you saw Sarah's post or my post, part of the reason that we're bringing this up is it's something that is just not well addressed. We don't spend enough time talking about time series when they're extraordinarily important and they come up very often in data science roles. So this is just a listing. There could be hundreds of these about where time series show up. But in general, the point of this slide is they're everywhere. They're much more prevalent than a lot of the things that I spent time learning in grad school. So I also want to draw a distinction between time series analysis and time series forecasting. Okay? Time series analysis to me, is much more about looking back. You want to be able to look at things and look at, you have much more of an explanatory focus. Okay? Time series forecasting, which we're setting things up for time series forecasting today, is going to be about generating a model, much more predictive focus. Okay? So both of these are important in their own right, but they involve different techniques and ways of thinking. So we're going to do some more definitions. Stochastic process. Okay, we're just going to define it as a sequence of random variables, flipping a coin. Yeah, the example that I hate using, that's always going to be used anyway. So a stochastic process is just a sequence of random variables. Flipping a coin is an example of one of these processes. A sample path, and you'll see why this matters in a little while. A sample path is one sample from a stochastic process. So let's say that we flip a coin 6 times, right? This is one example. Heads, tails, heads, heads, tails, tails, right? That's one sample path. There are an infinite number of different sample paths as you continue to do this and flip a coin over and over again, okay? So white noise, moving average, and random walks are examples of these stochastic processes. Okay, it's not flipping a coin, but the analogy still holds. These are the 3 that, if you start working with time series, that you should see most often. They form the building blocks for doing most time series analysis. How many of you, I'm curious, have actually heard, wow, so this is what happens when you start clicking upside down and you're like, which direction am I going? How many of you have heard any of these 3 terms before? White noise, moving average, random walks. All right, more than I thought. That's a good thing. Did this not show up there? I'm so confused about what's going on right now. Okay, so white noise is probably the most boring one, but also the most important. We're going to define y sub t as, and all of our notation, y sub t will be an outcome. It'll be the stochastic process. Okay. So the key with white noise is that we don't have correlation between observations. Okay, that's something to keep in mind. One of the fundamental properties of white noise is there's no correlation between observations. So again, we're going to get into some definitions here, and I'm happy to dig into this more, but when we talk about a normal distribution, you guys have a general idea what I'm referring to, okay? If I just go like this, it should ring some bells. So we're going to assume E sub t is normally distributed over 0, 1, okay? So over 0, 1, that we're looking at a normal distribution over the interval from 0 to 1, and IID, again, this is not going to turn into a stats class. We're talking about independent and identically distributed random variables. Okay, so that so E1 is independent of E sub 2, is independent of E sub 3. They all have the same distribution. Okay, so we're just, in this case, we're going to define y sub t is just equal to E sub t. So E sub t can take on a value of 0.01, 0.5, 0.73. Could it take on a value of 1.5? No, right? It's not within that interval. So a white noise process satisfies 3 things. And again, a lot of this is beyond, like it requires going much deeper in some of the mathematical proofs, which I'm happy to talk about, but you don't want to see that. The mean, or the expected value, of a white noise process is constant. Okay. The variance of a white noise process is also constant. And the autocovariance is 0. Okay. I'm not going to worry about trying to define these right now, but you should remember that whether or not the mean and the variance are constant is really important. Okay? Them being constant sets us up to do some important things. So this is a sample path for some white noise. Okay? So if you were to look at this, so what we're saying is this is white noise, and every single observation here is independent of the other observation. Does that seem like a reasonable assumption, given what we see here, that one point doesn't really tell you much about what the next point is going to be? Right? I mean, but something to keep in mind is it's still difficult to eyeball test that. Right? We can sit here and agree and be like, yeah, these lobes can be independent of each other, but we're really bad. We look for patterns and find patterns in anything. And so just saying, even if we completely agree on something, in a lot of cases we'd be entirely wrong anyway. So what we're going to dig into, not today, but in the future, is how do we actually think about whether our assumptions are correct. All right, so now we have a bunch of sample paths. Okay, so if we actually broke this down, right in here, I can't remember how many sample paths I generated actually. I think it was 10. I'm just guessing. No, I don't have any idea. But basically, each different color represents a sample path. Okay? So what you can see is, even though, so for each sample path, it's different than the previous one, but on the whole, they behave very similarly. Okay? Even though the values are a little bit different from each other, the general behavior looks pretty consistent. Sarah put the slide in, so I'm going to make her explain it. Because this is just how we are doing things.
Okay. So essentially, since white noise exhibits very random, erratic patterns, it doesn't make sense to try and model it, right? And so it's pretty straightforward.
Yeah. I don't take credit for such amazing visualization. So I just had to hand it off to her.
We moved away from slides and into our markdown, and I had to put up these slides.
Yeah, she loves the images. Right? Because again, this idea that we could go back here and we could fit a model to this. Right? You could fit a linear regression model to this. Not a good idea, but you could still do it. Right? But there's no point in doing that. White noise is just random observations. The second stochastic process is moving average. Yeah, so we're defining E sub t in the same way, except now Y sub t, instead of just being defined as E sub t, is going to be 2 consecutive observations. It's the average of those 2 consecutive observations. Okay, nothing too crazy. Definition's not very wild. This is a moving average stochastic process. You can take my word for it. That's a dangerous thing to do, but there is correlation between these observations. Okay, so Y sub 1 is not independent of Y sub 2. It's not independent of Y sub 3. There's correlation between them. So let's take a look at a sample path. So if I showed this to you, it doesn't look that different from white noise, does it? Someone always says yes, right? Someone, yes, it looks very different. No, if I had shown this to you right after I presented white noise, you would have been like, sure, yeah, those aren't related to each other at all. So this is intended to not only emphasize that that what a moving average looks like, but that the eyeball test is not a good approach to diagnosing whether there's correlation. There is correlation. It's not extremely severe in this case, but there is correlation between observations. But again, just by looking at it, it wouldn't be unreasonable for somebody to say, hey, that looks kind of like white noise. Right? Because it doesn't look so different. And this is where the idea, and probably what got me most interested in time series in the first place, is that we are really bad at looking at trends because we diagnose patterns where they don't exist, right? We don't think, when we look at a curve, we think about this as being the only possible outcome from the sequence of events that have occurred, right? We look back and we say, all right, well, it's been trending up. That means it should continue to trend up, right? But it's possible that a lot of factors just have generated the situation we see now. And if we ran the same events again, we could generate entirely different observations. But that's something, one, that is not a very comfortable thing to explain. When you're saying, oh, just because you see the curve going up doesn't mean that's a good thing. That's a hard thing to sell to an executive audience. When they're like, well, things are going up, right? They're going up. Well, maybe, maybe not. Okay, the last piece here is a random walk. Okay. So what we're doing now is y sub 3 would be the sum of E1, E2, and E3. Okay, so we're continuing to add on. And it makes sense that y sub 3 is not independent of y sub 2, right? Because they involve the exact same terms with each other. This is called a random walk. So this should look a little more familiar. When I said before that random walks often correspond to what we talk about with the stock market, right? Or very often stocks are best represented using random walks. This would be an example, maybe a good example. Hopefully you made this investment versus not making this investment. But if you look at this, you would say, all right, yeah, this is good. This is going up, right? And what's interesting is this is one sample path. So what do the other sample paths look like? So we saw one. We saw one sample path. It appeared to indicate things are going up, things are going well, right? But what we're saying is that with the underlying process, anything could have happened here. Could have gone down, could have stayed relatively consistent, could have gone up. So this is something that I want you to take away from tonight with time series, is that part of the idea, if we had done a simple curve fit here, right, we would have generated a regression line, whatever model you use, that eventually trended it up. Right? But in actually using a time series approach, where we try to understand what was the actual stochastic process that generated this path that we see, that gives us the power to say, no, something that's just trending perfectly up is not the right solution. It could, essentially anything could have happened. This is also why people get very frustrated by looking at stock charts over time, right? The variability that's possible is enormous, but we tend to see, it's a very weird way of thinking, to say, all right, the observations we're making are just one of many possible outcomes that actually happen. And that is a weird way of thinking compared to the curve fitting that we've had up to this point. Okay, so why is it important? We're talking about white noise, moving average, random walks. The truth is, we only have one sample path ever. Right? We have one set of observations. If you're in a business, they're not going to generate, oh, these are multiple different outcomes. They're just going to be able to show you this is the price over time. And so the beautiful thing and hard thing about time series is we have to use those observations to try to infer what the underlying process was that generated this one sample path that we're seeing. So our goal is to say, and this is the goal in all the cases where we're working with time series, is we're using this sample path to say, what was the process that actually generated this sample path that I see? Was it white noise where I'm just seeing random fluctuations? Was it a random walk? Was it a moving average? In a lot of cases, when we start talking, when you hear people toss around things like a Riemann modeling and ARMA modeling and stuff like that, it's a combination of different stochastic processes. That's not the focus of tonight, because it's very difficult to say anything meaningful about something like a Riemann or ARMA without understanding what the fundamental building blocks are that underlie this. We're not fitting lines to data. And that's the thing that if you walk away with one thing from tonight, it's this idea that the time series are not perfect. We are trying to use the sample path we see to understand what the process was that generated that one path that we've observed. So how does this work? And this is setting up for where we'll jump into next time, is we observe a process to a specific point in time, right? Like Q4 of last year or something like that. And then based on what we've seen thus far, we determine what are the most likely sample paths from that point on, right? So we use the data that we've generated thus far to decide what the stochastic process is. And from there, we can then do forecasting into the future. Say, now that we've decided what the underlying process is, what are the possible paths this process takes as we go forward, right? So if you had, so if we looked at an example, and let's say that we decided, like, up to this point, so our real observations only went up to this point. And we wanted to say, all right, so there are a whole bunch of sample paths that, let's say our real data ended up here. None of these curves actually do, but our real data brought us to this point. We would want to know, based on our observations up to this point, what are all of the sample paths that come after this point? And that's what forecasting is all about. That's why when we talk about forecasting, and if any of you have ever done anything like array modeling, the idea is that you start to project based on the sample path that you've inferred from the data that you have already. Forecasting is hard. It often looks frustrating and inaccurate because it looks like anything could happen essentially, which is true, right? Just because you're doing a time series doesn't mean that you're doing really accurate or really precise predictions. So I can't talk about time series without talking about stationarity, but the mathematical definition behind it is not worth putting up here for my sanity and yours. We care about things like the mean and the covariance. So when we're talking about stationarity, we are talking about the expected value of the mean, the expected value being constant, and the variance being constant. Okay, those things matter a lot to us. That sets us up to do a lot of powerful things. When you meet those two assumptions, time series modeling becomes a lot easier. If you don't meet those assumptions, things get a little messy. And the people who taught me time series would yell at me because what I just summed up is like actually like a 5-week discussion of why that's true. But just know that it's a very common assumption in time series modeling. Okay, so we're going to close with an example here. We're going to assume now that our stochastic process, right, we've discussed different ones up to this point, which are relatively simple. Now we're going to assume our stochastic process, this looks just like a linear regression, right? If any of you have done linear regression, we have beta 0, beta 1 as the estimators, and x sub t. And x sub t is our time series, so we expect the value is 0, and we're going to assume it's stationary. Okay. So if we do this, so we're going to look at our data here. Again, this doesn't look like clearly. We know that we can fit a line, and the line is probably just going to go through the middle of a lot of the points, right? But that's not going to stop us from doing it, right? So if we actually generate you can take my word for it here, that when we actually do the linear regression, so what you're seeing here, what I generated This is a set of random observations that I generated in R, okay, according to a specific, with specific coefficients. Those coefficients that I used were 25 for the intercept and 3 for the value of t. Okay, so that was the process that I used to generate the points that we saw. And when we actually used linear regression, it wasn't super bad, right? It got close on t, and we'll call it okay with coming up. Like it estimated 30, the actual value is 25. So, question is, okay, it did a decent job. Why did it do that? So, what we'll see, and this is an example that sort of is a prelude to what we'll cover next time, is that because we have a stationary time series, we get nice things that happen like this, where we can sometimes get close to the original situation. But let's look what happens when we try to do this with a random walk. Okay. A random walk is not stationary. Okay. So we're going to let's look at the data here. Right? Just like before, you can imagine if you just visualize, all right, I'm going to put a straight line through all of these points. Is it going to go well or not go well? By this point, you should probably assume it's just going to go badly. Because otherwise, what would be the point of me doing this, right? So, linear regression fails very badly. Okay, let's think about why that is. Or what in this output indicates that it fails very badly. What it's telling us is that this parameter t is significant. Very significant, right? This is a p-value is essentially no different from 0. But we already know with a random walk that there should not be a trend. Okay? A lot of this is, so part of why I'm skipping over a lot of the mathematics that sits under this. With a random walk, we should not see a trend. But linear regression clearly tells us there is one. And so this is what you start to see when you use curve fitting approaches for a lot of things that are better suited for time series, is you start to see erroneous conclusions. Like, this parameter is significant, or this model is actually good. It's not. It leads down the wrong path. That was not a really bad joke. So, this is what's called spurious regression. And so it's returned a significant result or told us that something is important when it's not. There are some details behind this as to why it happens. It has to do with standard error. But at the core, a random walk does not follow linear regression assumptions. What is that key assumption that it doesn't follow? Independence, right? The dependence of all of the observations produces very bad things when we try to use linear regression to fit a random walk. I didn't put a slide to let myself know that it's actually over, and now I'm just like, I guess it's over. So the point of going through what we did tonight, I know it's not sitting here fitting super fancy models, it's not applying code and looking at this real data, but when you're doing modeling, this is implicitly what's going on under the hood. You're using these different processes. You're trying to determine, when you see a time series, can I explain this time series through a combination of white noise, moving average, random walks, and some other processes that we'll look at. That's the goal. So when in the next session, when we do talk about time series, whenever we schedule that, when we talk about things like ARMA modeling and ARIMA modeling, when you do something, like you hit the function auto.arima in R, it returns results, right? Just like you've seen. But it's really important that you understand how it's generating those results. When it gives you these different parameters, it's trying to help you understand that it's made up of these different underlying stochastic processes. That's what arima modeling is doing, and it's really great. But what I see happen most often is people see something that auto out of arima, and they start this model fitting without understanding what it's doing. This is very similar to the analogy I use is if we have linear regression, right? You're just blindly applying linear regression without checking assumptions. You might get something that mattered, that it looks significant, but if you didn't actually look at any of the key assumptions in the modeling process, you're in trouble. Same thing happens here when we're doing arima modeling. Understanding what's going on, the assumptions we're making, and what comprises an arima model helps us actually better make sense of what this arima model is. So that is what we will pick up on next time when we move into more of a forecasting mode. And yeah, so thank you guys very much for coming out tonight. And we'll be around for a little while. And yeah, I'm not just going to cut you off on the stage. Yeah, Sarah would like to answer your questions. Any questions that you guys have?
Everything makes sense.
No, see, this is what happens. Time series doesn't make sense until the 7th time you've done it. But what I recommend, if you are curious about time series, the resources we provided are really good. I think they're a useful way for you to break things down. I've found, actually, for my own purposes, data camps courses on time series are pretty solid. Their intro to time series course is, I believe most of it is free, but again, it's very useful. They have nice little like 5-minute video discussions, and you actually do some live coding. So if you're curious about getting started on this, those are some resources that I would suggest using. And it's a different, and there's one last thing that I want to close with the time series, is when you start doing this in a business setting, it's one thing to sit here and do time series modeling, to come up with what the underlying model is. It's another thing to then be able to walk in to a presentation and say, oh yeah, you see that trend that's going up? It's not actually like necessarily a good thing. It's actually just one, like this is just random noise that we're seeing. Telling somebody that they're seeing random noise when they think they're seeing a good business outcome, that's where you find out if you're actually analytics driven. If you're comfortable, if someone is comfortable saying, all right, I can buy into that. Because most often, that is an unpleasant conversation. But I've seen it happen a lot of times, and you will continue to do that. So that's something that I encourage you to consider about what that, learning about this is great. Learning about what time series is helpful. But there's another dimension to it, being able to put it into practice and actually make recommendations to people. And that requires a whole other skill set, one which I'm still trying to develop. I'm going to kill your hopes and dreams where you thought this product was doing well and it's not. But just things to consider, and Sarah and I will be around for a little bit. Thank you guys so much for coming out, and we'll see you next month, okay?
All right, and I'll post, actually, for some of you who know that all my slides and all stuff is available online. If you want to go onto my GitHub, or I'll post it on the meetup page so that you guys can have access to everything. Cool. All right, you guys rock!
Can we stop the recording?
I will.